Welcome to the deep dive. Today we're plunging into the really fascinating world of stereochemistry. We're using Organic Chemistry I for Dummies, Chapter 6, as our guide. And trust me, you're going to discover how these tiny, tiny twists in molecules can have, well, huge effects in the real world. Let's kick off with something familiar, maybe surprisingly so. Smells. Imagine you've got two molecules, exact same atoms, connected in the exact same way. You'd think they'd be identical.
That seems logical, yeah.
But take lemon. It's pretty common. One version, one 3D shape, smells exactly like oranges. Its twin, those same atoms, same links, smells like lemons. How is that even possible? It's kind of mind-bending when you first hear it.
It really is. And what's fascinating here is just how fundamental this whole concept is. It touches everything, from, like you said, smell, right up to the building blocks of life.
Life itself.
Absolutely.
Yeah.
Nature relies on incredibly specific 3D shapes. Think about proteins, sugars, DNA, RNA. Their function is totally locked into their three-dimensional structure. And this carries right over into medicine. Most drugs, they only work in one specific 3D form.
It's just one form.
Just one. Other forms, even with the same atoms hooked up, might do nothing at all. Or worse, they could be harmful. We'll actually get into the really sobering story of thalidomide later on. It makes this point tragically clear.
Wow. Okay. That definitely sets the stage. So our mission today for this deep dive is to figure out how we actually, see molecules in 3D. How do we tell these different 3D forms apart? And what are the sort of core ideas, the language and the real-world consequences of it all? It's about going beyond those flat drawings we usually see. Okay, so first hurdle. How do you draw something 3D on a flat piece of paper or a screen? Chemists came up with a system, a visual code almost. You use solid wedges, kind of like little triangles, for bonds sticking out at you.
Coming out of the page.
Exactly.
Yeah.
And then you use dash wedges, like dash lines, for bonds going back, away from you, into the page. Normal lines, those are just flat, lying in the plane of the paper. It's pretty neat, actually. It lets us depict these shapes.
Yeah, it's a crucial convention. And building on that visualization, we need to start classifying molecules based on these spatial differences. The lemon example you gave, that's perfect for stereoisomers.
Stereoisomers, okay.
These are molecules with the exact same atom connectivity, like A is bonded to B, B is bonded to C, same sequence. But they just differ in how those atoms are arranged in 3D space. Think of them as, well, mirror images sometimes.
Ah, okay. Different from constitutional isomers, right? So I think we touched on those before.
Exactly. Constitutional isomers have the same formula, like C4H10, but the atoms are connected totally differently. It's a different structure altogether. Stereoisomers. Same connections, just a different 3D layout.
Got it. The classic analogy really helps me here. Your hands are kind of like stereoisomers, aren't they? They have the same fingers connected in the same order, thumb, index, middle, etc.
Same basic blueprint.
But try putting your right hand perfectly on top of your left, palm to palm, matching everything up. You can't do it. They're mirror images, but they're not superimposable. That's stereoisomers.
Perfect analogy.
Now, if, like, your thumb was swapped with your pinky on one hand, that would be more like a constitutional isomer. The actual connections would be different. It really highlights how subtle these 3D differences can be, but how important they are.
And that hand analogy leads us straight into enantiomers. Enantiomers are specifically molecules that are non-superimposable mirror images of each other. Your right hand is the enantiomer of your left hand.
Okay, so enantiomers are a specific type of stereoisomer.
Exactly. They are stereoisomers that have that mirror image relationship but can't be overlaid perfectly. Which brings up a key question. How do we know if a molecule will have an enantiomer? Or is its mirror image just identical?
Right, because not everything has a distinct mirror image twin. That's where chiral and achiral come in, I think.
Precisely. A chiral molecule is one that cannot be superimposed on its mirror image. It has handedness, like your hands. Think of a carbon atom bonded to 4 different things like bromine, chlorine, fluorine, and hydrogen. That molecule is chiral.
And achiral.
An achiral molecule can be superimposed on its mirror image. Its mirror image is actually identical to the original molecule. Methane, CH4, is a simple example. 4 identical hydrogens. Its mirror image looks exactly the same. You can spin it around and it lines up perfectly.
Okay, so the rule is only chiral molecules have enantiomers. Achiral molecules don't.
That's the fundamental rule. Now, how do we spot chirality quickly without drawing mirror images all the time? We look for chiral centers. You might also hear them called stereogenic centers.
Chiral centers, okay, what are those exactly?
Typically, it's a carbon atom that's bonded to 4 non-identical groups or atoms, 4 different things attached. If a molecule has one chiral center, it's almost always chiral itself. There's one important exception, which we'll get to.
Good to know. Any tips for spotting them?
Yeah, a couple of quick checks. Carbons in simple chains like CH3 or CH2 groups, they can't be chiral centers because they have identical hydrogens. 2 or more hydrogens means not 4 different groups. Also, carbons in double or triple bonds, they can't have 4 separate attachments, so they're not chiral centers either. These little shortcuts help you quickly scan a molecule and find the potential points of handedness.
Okay, that's useful. So say we find a chiral center. How do we actually describe its specific 3D arrangement, its handedness?
Oh, yes. For that, we need a naming system. It's called the RS nomenclature. R comes from the Latin rectus, meaning right. S comes from sinister, meaning left.
Or right and left. Okay.
It's a standardized way to assign an absolute configuration, a specific label to each chiral center. Critically, if the chiral center is R in one molecule, its enantiomer, its mirror image, will have that same center designated S.
So it distinguishes between the mirror images. That seems vital,
Yep.
especially for drugs, like you said earlier.
Absolutely crucial. And there's a specific method, the Cahn-Ingold Prelog rules, to figure out if a center is R or S. It involves 3 main steps. First, you prioritize the 4 groups attached to the chiral center,
Prioritize. How?
based on the atomic number of the atom directly connected to the chiral center. Higher atomic number means higher priority. So bromine beats chlorine, chlorine beats fluorine, fluorine beats oxygen, and so on. Hydrogen with atomic number 1 is basically always the lowest priority, number 4.
Okay, prioritize by atomic number. What's next?
Second, you mentally rotate the molecule or redraw it so that the lowest priority group, usually hydrogen, group 4, is pointing away from you, into the page, like it's at the back.
Uh-huh. That sounds like the tricky part, the visualization.
It can be, definitely takes practice. But once group 4 is in the back, you do step 3,
Yep.
draw a curve, trace an arc from the highest priority group 1 through the second 2 to the third 3, ignore group 4 back there. If that curve goes clockwise, the center is R. If it goes counterclockwise, the center is S.
Clockwise R, counterclockwise S.
Got it.
But yeah, that rotating part.
It is tricky, which is why chemists have developed some clever workarounds or tricks to help. For example, there's a swap rule. If you swap any 2 groups on a chiral center on paper, you invert its configuration. R becomes S, S becomes R.
Interesting.
So sometimes, if number 4 isn't in the back, you can do a swap to put it there, figure out R or S, and then remember to flip your answer because you did one swap. Or even better, a double swap. Swap 4 with the group in the back, then swap the other 2 remaining groups. 2 swaps cancel out, so whatever RS you get after the double swap is the correct original configuration.
Okay, that sounds less error-prone, maybe.
It can be. There's also a rule for when group 4 is pointing towards you on a solid wedge. You can just determine the 1, 2, 3 direction as usual, but then you take the opposite answer. Clockwise means S, counterclockwise means R if 4 is in front.
Handy shortcuts. It shows how people find ways to manage this 3D thinking on 2D paper.
Exactly. Tools to make it systematic. Now, earlier I mentioned an exception to the rule that molecules with chiral centers are chiral.
Right, you did.
That exception involves meso compounds. A meso compound is a molecule that actually contains chiral centers, but the molecule as a whole is achiral.
How can that be? Chiral centers, but the molecule isn't chiral.
It's because it has an internal plane of symmetry. Imagine a mirror plane cutting right through the molecule. If that plane divides the molecule into 2 halves that are mirror images of each other, the whole molecule is achiral, even with chiral centers present. The internal symmetry cancels out the handedness.
Okay, an internal mirror plane. Can you give an example?
Sure. Think about cis-to-bromocyclopentine. It's a 5-membered ring with 2 bromanes on the same side. It has 2 chiral centers, but you can draw a plane of symmetry right through the middle of the ring between the carbons with the bromines. 1 half reflects onto the other, so it's meso, it's achiral.
And its mirror image would be?
Identical,
Yeah.
superimposable. Now compare that to trans-d-bromocyclopentane, where the bromines are on opposite sides. It also has 2 chiral centers, but there's no internal plane of symmetry, so the trans version is chiral. It has a non-superimposable mirror image and an enantiomer.
I see. So the symmetry is key. Even with chiral centers, if the whole molecule is symmetrical like that, it's achiral, it's meso.
Precisely. Now, let's shift from structure to a physical property we can actually measure. Chiral molecules have this unique ability. They can rotate plane-polarized light.
Plane-polarized light, what's that?
Think of normal light waves vibrating in all directions. Plane-polarized light is filtered, so the waves vibrate in only one single plane. like through polarized sunglasses. If you pass this special light through a sample of a chiral compound, the plane of light gets rotated either to the right clockwise or to the left counterclockwise.
And only chiral molecules do this.
Only chiral molecules. Acromolecules, including meso compounds, do not rotate plane-polarized light. They're optically inactive. Now, here's a crucial point about enantiomers. They rotate plane-polarized light.
Let me guess, in opposite directions.
Exactly. In equal amounts, but opposite directions. If one enantiomer rotates light plus 30 degrees, its mirror image twin will rotate it -30 degrees. And importantly, the R or S label doesn't tell you the direction of rotation. R could be plus or minus, S could be plus or minus. You have to measure it experimentally.
Okay, so RS is structure plus Enantis is observed rotation. Got it.
Right. And this leads to the concept of a racemic mixture. That's simply a 50-50 mixture of two enantiomers. Since you have equal amounts of the plus rotator and the rotator, what do you think happens to the overall rotation?
They cancel out. Zero rotation.
Exactly. Racemic mixtures are optically inactive. The rotations cancel perfectly, resulting in a net rotation of 0. This property is super useful in the lab for identifying and characterizing samples.
Okay, that makes sense. So we've covered single chiral centers, meso compounds, optical activity. What happens when you have more than one chiral center in a molecule that isn't meso?
Good question. Things get a bit more complex, and we encounter another type of stereoisomer, diastereomers. Diastereomers are stereoisomers that are not mirror images of each other.
Not mirror images. How does that work?
It usually happens when you have two or more chiral centers. Let's say a molecule has two chiral centers. We can use the 2n rule. N is the number of chiral centers. So 2n tells you the maximum number of possible stereoisomers. With two centers, n and 2. So 22 equals 4 possible stereoisomers.
4 different versions of the same molecule structure.
Wow, potentially, yes. Imagine the configurations could be RRS as RS and SR. Now, the RR and SS molecules are mirror images of each other, right? They are enantiomers. And the RS and SR molecules are also mirror images of each other. Another pair of enantiomers.
Okay, 2 pairs of enantiomers. So where do diastereomers fit in?
The relationship between a molecule from the first pair and one from the second pair. For example, what's the relationship between RR and RS? They are stereoisomers, same connectivity, but they're clearly not mirror images. One center is the same R, the other is flipped RS.
So RR and RS are diastereomers, and RR and SR are also diastereomers.
Exactly. Diastereomers are stereoisomers that aren't enantiomers. They have different physical properties, unlike enantiomers, which are mostly identical except for light rotation. You can see how quickly the possibilities multiply.
Yeah, 4 isomers from just 2 centers. Trying to draw and compare all those using wedges and dashes sounds challenging.
It can be, which is why, especially for molecules with lots of chiral centers like sugars, chemists often use Fischer projections. It's a specific way to draw molecules in 2D that makes visualizing multiple chiral centers much easier.
Fischer projections. Okay, how do they work?
You basically represent each chiral center as a cross, an intersection of a horizontal and a vertical line. The convention is that the horizontal lines represent bonds coming out of the page towards you, like wedges. And the vertical lines represent bonds going back into the page away from you, like dashes.
Okay, horizontal out, vertical back. Got it. Seems simpler than wedges and dashes everywhere.
It is, especially for chains of chiral centers. Every cross is a chiral center. There are specific rules for manipulating them. You can rotate the whole projection 180 degrees in the plane of the paper, and it's still the same molecule. But not 90 degrees, that changes it. You can also hold one group fixed and rotate the other 3 around it.
And you can still figure out RS from these.
Yes. You assign priorities as usual. Then the trick is often to make sure the lowest priority group, number 4, is on a vertical bond. Top or bottom, meaning it's pointing back. You might need to use allowed rotations to get it there. Once a number 4 is vertical, you look at 1, 2, 3. Clockwise is R, counterclockwise is S, just like before.
So they're really useful for comparing isomers.
Incredibly useful. You can stack Fischer projections next to each other and easily see if they're mirror images, enantiomers or not, diastereomers. And spotting meso compounds becomes much easier too, because the internal plane of symmetry often becomes visually obvious in the Fischer projection.
Okay, that's a practical tool. Now, you mentioned earlier a sobering real-world case, thalidomide. Let's go there. Why is it such a critical example in stereochemistry?
It truly is. The thalidomide story from the late 50s, early 60s is, well, it's why understanding stereochemistry is non-negotiable in medicine now. It was prescribed mostly in Europe and Canada, to pregnant women for morning sickness.
Okay.
The drug molecule, thalidomide, is chiral. It has one chiral center, but crucially, it was sold as a racemic mixture.
A 50-50 mix of both enantiomers.
Exactly, a 50-50 mix of the R form and the S form, and here's the tragedy. One enantiomer, let's say the R form, was effective against morning sickness. It did what it was supposed to do. But the other enantiomer, the S form, was a potent teratogen. It caused horrific birth defects, primarily phocomelia, severely stunted limbs in thousands of babies born to mothers who took the drug.
Oh my God. Just because of the mirror image molecule.
Just because of the mirror image molecule, it interacted differently with biological systems in the developing fetus. And why was it sold as a mix? Well, back then, large-scale synthesis often produces racemic mixtures naturally. And separating enantiomers, as we touched on, is really difficult. They have almost identical physical properties: boiling points, melting points, solubility. Standard separation techniques often don't work well.
So it was easier and cheaper to just sell the mix.
It was standard practice at the time, largely because the profound biological difference between enantiomers wasn't fully appreciated or easily managed chemically. Separation can be done using chiral techniques, but it adds significant cost and complexity. But thalidomide, it forced a reckoning. It raised the urgent question: what did we learn, and how must drug development change?
This sounds like it changed everything.
Fundamentally. It led to much stricter regulations worldwide regarding the testing and approval of chiral drugs. Now, pharmaceutical companies generally have to test enantiomers separately, understand their individual effects, and often market only the single beneficial enantiomer if the other is inactive or harmful. Stereochemistry became central to drug safety and efficacy.
What a powerful, devastating lesson. It really brings home why understanding these 3D shapes matters so much. So we've really covered a lot of ground today. We went from just trying to draw molecules in 3D to learning the RS language, telling apart isomers like enantiomers and diastereomers, spotting symmetry in meso compounds, even looking at how they interact with light, and finally understanding the absolutely critical real-world impact, like with thalidomide. It's clear the shape is everything.
It really is. This deep dive into stereochemistry, I think, truly highlights that handedness at the molecular level isn't some minor detail. It's often the absolute key to how a molecule functions, how it interacts with other molecules, especially biological ones, and whether it's safe or dangerous. It forces you to think beyond just the formula, beyond just the connections, to how the molecule actually occupies space.
Yeah.
And it makes you wonder, doesn't it, what other secrets are waiting to be unlocked by understanding these 3D structures even better? In biology, in new materials, where else will this perspective lead us?
Absolutely. It gives you a whole new appreciation for the precision and maybe even the artistry of chemistry at that tiny scale. Well, thank you for joining us on this deep dive into the world of stereochemistry. Until next time, keep exploring.